Now let's talk about the concept of normal distribution. We had a detailed discussion on normal distribution in the quantitative portion, but let's just recall it further. So this whole mean variance optimization approach is based on the assumption that whatever returns we have, they follow the normal distribution. So there is this assumption, a very strong assumption behind the whole formula of the MVO framework, that returns follow a normal distribution, which is also a true example because returns generally follow a normal distribution. Now, the normal distribution is one of the most well-known and widely used probability distribution because most of the distributions, when n increases, they tend to follow normal distribution. So basically, in statistics and econometrics, all of the distributions that we studied in the probability distribution, they actually follow the normal distribution when n is large, and it's just a derivation of the normal distribution, and hence the normal probability distribution is widely used in all of the fields, but more specifically, it's more pertinent to the finance and risk management. Now, normal distribution, it's a symmetrical distribution as can be seen in the graph, and we also call it a bell curve because it forms a bell-like thing. Now we call it symmetrical because the left side of the distribution is exactly equal to the right side of the distribution. This is almost symmetrical. We have some issues with skewness of the distribution, which we will just shortly discuss, but a simple normal distribution in its truest form is symmetrical, that is, left hand side is actually exactly equal or the mirror of the right hand side. Now whenever we plot a normal distribution, there are a certain assumptions that we can make about it. So the first thing is pertaining to the observations that fall with a certain standard deviation. So here we have the mean of the distribution. In some of the cases in a standard normal distribution, we generally consider it as 0, and this S represents the standard deviation of the distribution. So basically, based on a symmetric normal distribution, we can see that 68% of all observations fall within plus minus 1 standard deviation. So basically, if we have 100 observations in a data, about 68 would fall in this particular region here. If we increase the area by 2 standard deviation, the number of observations increase to 95%. So from here to here, the number would be what? 95%. So basically what we are saying that, for example, we have data about marks of students in grade 2. They have a mean of 80 and they have a standard deviation of 5. So if we add 80 plus 5, it will come out as 85, which is the upper bound, and if we subtract 5, it will come out as 75. So based on this normal distribution, if the marks follow a normal distribution, about 68% students would lie between 75 and 85 marks. Similarly, for 2 standard deviation, it will be equal to 80 plus 10, which is 90, and 80 minus 10, which is 70. So 95% of the students will fall between 70 and 90, and for the third standard deviation, this is first, this is second, and for the third standard deviation we can have 80 plus 15, which is 95, and 80 minus 15, which is 65. So 99% of the students would be between 65 to 95. Okay, so what we are doing, we are just taking the mean and we are adding one standard deviation. Then we multiply standard deviation by 2 and add it, and then we multiply it by 3 and add it to the mean. So this is how normal distribution operates. So these 1, 2, 3 are broad numbers. If we talk about the precise numbers, about 90% of the observations actually lie within 1.65 standard deviation. About 95% lies in the range of about 1.96 standard deviation, and about 99% lies within about plus minus 2.58 standard deviation. So this is how we describe the normal distribution, and that's why it's one of the mostly used distribution, because it can be applicable for most of the cases, especially when we have a higher number of observations. Now let's talk about some of the characteristics of normal distribution. So normal distribution, one of the advantages of normal distribution is that it can be described by only two parameters. So basically we are just concerned about mean and variance of the distribution, and the x can be defined as mu comma standard deviation. And of course it's a simple advantage, because for any data, for any series of data, we can simply calculate the mean and the standard deviation, and once we do that, we can apply or we can check the applicability of normal distribution to that particular data. Then the normal distribution has a skewness of 0 and a kurtosis of 3. So basically a skewness mean is how left hand side is mirroring right hand side. So if it's exactly equal, we will say that the skewness is 0, which means that the distribution is perfectly symmetric. We can have cases where it can be either positively or negatively skewed, but in its truest form, a normal distribution is a symmetric distribution, and the kurtosis is 3, which means that it is very much aligned with the normal distribution. There isn't any problem of fat tails, there isn't any abnormality about the data. So basically the kurtosis is called the peak of the distribution. So if it has a higher kurtosis, it will look like this, and then we can have a problem of fat tails in the data, which means that we have more extreme observations, which creates issue with the interpretation of our results. Now, since the normal distribution is symmetric, the mean, median and mode for this particular distribution, they all are equal, and for the positive and negative skewed distributions, it varies. This is something that we discuss in detail in the quantitative section. Now let's discuss the concept of z-table. So if we want to calculate the probability of x, we can find it using the standardized values and probability table for z. How do we do that? We have a table available where we have different values for probability. If we have to find the probability of a standard normal variable, we will just find it out in the table. For example, we want to calculate the probability for x less than or equal to 0.5. So what will we do here? We will find 0 here, which is here, and we will move down and find 0.5 here. So the probability for 0.5 for x to be less than 0.5 for any particular case, of course we are talking about a very generic example, the probability would be 0.6915 or 69.15. Now if we want to calculate the probability of 0.03, we will just go down there at 0.03 and we will see the 0 because this is the value that we are interested in, and the answer would be 0.5120. So that's how we calculate the probability for given value of x in the z table. Of course this is a sample. For the z table, the actual z table is much larger and it has a lot of values which goes from 0 to about more than 3. Now these are for positive probabilities. What if we have to find probability for negative number? So since we discussed that normal distribution is actually symmetric, for a negative number we will just take n minus x. So whatever number we have for this particular distribution, we will subtract it from 1 minus nx. For x minus 0.5, the probability would be 1 minus 0.6915. That's how we calculate the probability for a negative number using the z table. Now let's talk about some of the limitations of normal distribution. The first and the most critical limitation that we have is that we can have cases when financial variables show a problem of fatter tails. So basically what happens is that normally we have a distribution like this, but we can experience a data where normal distribution is something like this. Now when we have such a case, we have more observations in the tail. It means that we have more extreme values. It means that we are assuming it to be normal and we are expecting that about 1% observations would be coming in the tails of the distribution, which means that 1% of the observations would be extreme. For example, if we had marks for grade 2 that we just discussed, we are assuming that only one student would have a mark that would be more than 95 and less than 65 based on normal distribution. But if we have fatter tails, we can have more chances that it can increase to about, let's say, 2% or even 5%. So basically it's a deviation from normal distribution as we have more and more students who are scoring in extreme, which is either more than 95 marks or less than 65 marks. Now this problem of fatter tails increase the probability of adverse extreme events that we just discussed, and that's why the MBO framework becomes unreliable when we have the problem that normality assumption is not met and we have a problem of fatter tails. And hence we have to make sure that whatever distribution we are following, it is largely following the normal distribution and we don't have any deviation from it, because if we have such a problem, we would not be able to apply it to our data and we would not be getting reliable results.